Hi, my name is Ellen Vitercik, and I'll be presenting the paper Refined Bounds for Algorithm Configuration, the Knife Edge of Dual-Class Approximability. And this is joint work with Nina Balcan and Tuomas Sandholm, and we're all at Carnegie Mellon. And this paper was published this summer at ICML. Algorithms often come with a ton of tunable parameters, and these parameters can have a significant impact on the algorithm's runtime, its solution quality, and so on. Oftentimes, domain experts are left to tune these parameters by hand, a process that can be time-consuming, tedious, and error-prone. In this line of research, our goal is to automate the process of algorithm configuration using machine learning. So we want to be able to algorithmically find good parameter settings using a set of typical problem instances from the application domain at hand. And you can think of the set of typical problem instances as the training set. So at a really high level, this is what this automated algorithm configuration procedure would look like. First, we fix some parameterized algorithm, such as Cplex. Then we receive a set S of typical problem instances sampled from some unknown application-specific distribution D. We perform some optimizations, and then we return a parameter setting which has good average algorithmic performance over this training set. So by algorithmic performance, you can think of this as a measurement of the algorithm's runtime, its solution quality, its memory usage, and so on. The key question that we want to answer in this talk is, will those parameter settings we come up with also have good expected performance on this unknown application-specific distribution? Said another way, will those parameter settings also have good performance on future problem instances that we haven't already seen in our training set, but which are from the same application domain? So a little more formally, here is our model of algorithm configuration. I'll use the notation X to denote the set of all inputs to the algorithm. So for example, these could be integer programs. And RD will be the set of all parameter settings. So for example, these could be Cplex parameter settings. We're going to make a standard assumption that's made all the time in this literature on automated algorithm configuration, which is that there's some unknown distribution D over inputs to this parameterized algorithm. So for example, this distribution might represent the scheduling problems that an airline has to solve on a day-to-day basis. So a little more formally, what do I mean by algorithmic performance? I'll use the notation FR of X to denote the utility of the algorithm parameterized by R on the input X. So throughout this talk, I'll use the terms algorithmic performance and utility interchangeably. And again, you can think of this algorithmic performance function as measuring the algorithm's runtime, its solution quality, and so on. And we're going to assume that FR of X is bounded within the interval -1, 1, but our results can very easily be generalized to any bounded interval. A tool that we found really useful for analyzing algorithm configuration problems is the notion of a dual function. So for any input X, such as an integer program, the dual function, which I'll denote fx star, measures algorithmic performance as a function of the parameters. So this could be, for example, runtime on the input X as a function of the algorithm's parameters. So in this picture, you can imagine varying some parameter R along the horizontal axis, and we're plotting algorithmic performance on this input X as a function of the parameters. And we've noticed in a lot of domains that this algorithmic performance function can be extremely volatile, extremely choppy, but they are often well approximated by some simple function. So in this picture, this simple approximating function is this black dotted line. So even though fx star, the algorithmic performance function, is really choppy, it's well approximated by this simple piecewise constant function with only two pieces, which I'm denoting gx star for the input x. And we observe this behavior, for example, in the context of integer programming algorithm configuration. So with this notion of dual functions and approximability in mind, I'll tell you about the main result in this paper. So let's remember the key question that we want to answer in this talk, which is for any parameter setting R, if that parameter setting has good average utility over the training set, does this imply it will also have good expected utility on the unknown distribution? More formally, given samples x1 up through xn, sampled from this unknown distribution over problem instances, for any parameter setting R, what's the difference between that parameter setting's empirical average utility over the training set and its expected utility on the unknown distribution? We refer to this type of bound as a generalization bound because it tells us to what extent is average performance over the training set generalized to expected performance on the distribution. If indeed this difference is small for any parameter setting R, we know that if we find a parameter setting with good average utility over the training set, it will also have good expected utility on the unknown distribution. So here's the generalization bound that we present in this paper. We prove that with high probability over the draw of this training set, for any choice of this parameter setting R, the difference between its average utility over the training set and its expected utility on the distribution is bounded by this quantity. So the first term in this bound measures, on average over the training set, what's the difference between this true algorithmic performance function fx star and the simple approximating function gx star on average over all inputs x in the training set. And we're taking the L infinity norm here, which means we're measuring the maximum difference between the blue and the black function in this picture. This next term, at a high level, is a way of measuring just how simple these approximating functions actually are. So here G is the set of all functions gx star that we're using to approximate the algorithmic performance functions. And I'm not going to go into the details here, but specifically we use Rademacher complexity to quantify this term. Rademacher complexity is a really standard tool from machine learning theory. And if indeed this set of functions is simple, then this term is going to go to 0 pretty quickly as the number of samples n grows, as will the third term, square root of 1 over n. So now to demonstrate the utility of these bounds, we present a few experiments. So in these experiments, we tune the parameters of an integer programming solver. And in prior work by us and also Travis Dick, we provide worst case generalization bounds for tuning these parameters. And here the distribution over integer programs is related to a problem from auction design. So specifically winner determination in auction design. So in this plot, the blue line is our generalization bound from 2 slides ago. And the black dotted line is that worst case bound from our prior research. And we can see that our blue bound from this paper greatly improves over the worst case bound up until the point where there are about 100 million samples, at which case the bounds are about equal. Okay, so why is this paper called the Knifeedge of dual class approximability? To answer this question, I'll tell you about our second main result. So in this talk already, we've seen that if these algorithmic performance functions are well approximated by some simple function under the L infinity norm, which means the maximum difference between the blue and the black line is small, we're able to provide strong generalization bounds. If, however, this approximation only holds under the LP norm for some p smaller than infinity, then it's not possible to provide non-trivial generalization bounds in the worst case. So this means that the connection between learnability and approximability is balanced on the knife edge. There's this sharp dichotomy between the L infinity norm and the LP norm for p smaller than infinity. So now I'll just wrap up with a conclusion. In this paper, we provide generalization bounds for algorithm configuration. And our bounds apply whenever utility or algorithmic performance as a function of the parameters is approximated by a simple function. And we see that this is indeed the case in a lot of settings, such as integer programming and algorithm configuration. And we prove that the connection between learnability and approximability is balanced on a knife edge. So if this approximation holds under the L infinity norm, we can provide strong generalization bounds. But if this approximation only holds under the LP norm for some p smaller than infinity, it's not possible to provide non-trivial bounds in the worst case. Finally, we provide experiments demonstrating the strength of these bounds. Thank you.